We're going to continue talking about prime numbers in this segment, and most specifically, we're going to talk about how to determine whether a large number is prime or composite. And a couple things that we've said about primes in the last segment, so a couple things I want to remind you of. We said in that last segment on prime factorization, which remember prime factorization was referred to as the fundamental theorem of arithmetic, the most important thing I can say in arithmetic, right? That's the meaning of the fundamental theorem. And it told us that all numbers can be broken down into a product of primes. Or another way to say that is prime numbers are the building blocks of all other primes. And so in the classwork the other day, you had to find some additional factors of a number. We're going to talk about how nice it is to look at numbers in their prime factored form, because we'll be able to tell things about divisibility and factors, and we'll be able to really analyze the number when we see it as the product of its prime. So there's more of that coming up. But anyway, on the topic of determining if a large number is prime or composite. So I'm going to add in another definition of composite. All right, so we had a definition the other day of composite, but let me give you this one. Let me point out that composite, and you can tell just by the way it sounds, it means composed of primes, right? Composite, composed of primes. Therefore, if we're talking about any number, any whole number, right, greater than or equal to 2, so I've got a number greater than or equal to 2 because 1 and 0 are neither prime nor composite, right? And then we don't talk about, if we're talking about primes and composites, we're not dealing with decimals and fractions and negatives, right? We're dealing with whole numbers, right? But these two whole numbers are neither prime nor composite. So when we're referring to prime numbers, we're referring to numbers greater than or equal to 2. 2 is special in that it's the only even number that is prime. So anyway, we need to determine, is this large number 587, is that prime or composite? So it's composite if I can find a prime divisor, right? If it is composed of primes. Now, one of the things that we talked about in the last segment where I was getting you ready for this lesson is we were talking about how we take a number and we take that many chips or cubes or whatever, and we make a rectangle with it. All right, and each dimension of the rectangle is a factor. So every factor has a partner, right? Because how could I make a rectangle without having a length and a width? Right? Wouldn't be possible. A number might only have one divisor other than itself. For example, like the number 79, right? The only number that divides 79 besides 1 in itself is 7. But a number can be its own partner if I have a perfect square. All right, so 49 would be 7 units this way, 7 units this way. So the only time I can have like an odd number of factors is when the number partners with itself. All right, but it still has a partner, right? Every number partners with itself, or every number has a partner, even if the number partners with itself, which is only the case if I have a perfect square. So anyway, keep this in the back of your mind then as you go through and start to try to determine, is 587 prime? So it is a lot of work to determine if a number is prime, but what we need to figure out is how to do this with the least amount of effort possible, okay? Because when I'm looking at 587, I have to say, well, does it have a divisor, right? And then I have all these potential divisors, starting with 2, right on up until, I get to this quantity, right? So I have to consider, could any one of these numbers be a divisor? I don't know until I test. So it's possible, though, to cut my work way down, okay? One of the things that will help my work is to use some divisibility rules, which we haven't talked in depth about yet, but I'm hoping you know the basics, like for 2, for 3, and for 5. So I am actually testing for these divisors, right? I'm testing to see, well, does 2 go in? No, it doesn't because it's even. All right, so I didn't take my calculator out and divide, but I still checked for 2 being a factor. Does 3 divide? We reviewed that the other day. If the sum of the digits is divisible by 3. So if I add 5 plus 8 plus 7, I get 20. 20 is not divisible by 3, so 3 doesn't divide. It doesn't end in a 5 or 0, so 5 doesn't divide, right? Doesn't end in 0, so 10 doesn't divide. So those are some of the ones that I can check without having to grab my calculator. But what I want to know then is, should I take my calculator and divide by 4, divide by 6, by 7, by 8, by 9, by 10, 11, 12, 13, 14, 15? And also, should I, how far do I have to go? Like, and I put some dots here to show that I have every number between 29 and 100, right? So should I test 101, 102, 103, right? Should I test 217, 218, 219, 220, right? Do I have to test every number up to here? And this is where we really lose out not being in class, because right now you'd be in your groups, you'd be talking with your group members, and you would have that benefit. So I know that it's probably very tempting to not pause the video and just let me give you the answer. All right, but I'm really encouraging you to pause the video and start doing some dividing. All right, start dividing ones that you think you actually have to divide. So it is a lot of work. We are going to have to take our calculator and actually just do, 587 divided by 11 and see if we get a whole number answer. All right, so there is some work like that involved. But I want you to try to figure out, can I stop dividing at some point before I get up into here, or am I still testing numbers like 585, 586? Like, when can I stop? Okay, and that's something I'm hoping you can figure out. So please pause the video and think about this. Okay, so I hope you are unpausing after playing with this. Again, I'm trying to think if I would have the dedication to try to figure things out when I knew my teacher was just going to give me the answer in 5 minutes. I may or may not have that dedication myself. So I'm hoping you played around with this and figured some things out. It is pretty satisfying, I think, to figure rules out yourself. So a couple things I hope you realized, right? We tested 2, 3, 5. We didn't divide, right? But we did test for them. But do we have to test 4? Right? And the reason I don't test 4 is because a number would have to be even for 4 to divide it, right? 4 is made up of 2 and 2, right? So if 2 doesn't go into a number, no even could go into it. So that's where I could eliminate every single one of these potential divisors, right? So I just cut my work in half, right? I have eliminated half of the potential divisors because I've eliminated all evens, right? Because if 2 doesn't divide it, all of these even numbers, like if I think about 18, 18 is 9 times 2, so it's 3 squared times 2. 18 is made up of 2 3s and a 2, right? So if 2 can't divide this, then nothing composed of a 2 can divide it. Or if 3 can't divide this number, then nothing composed of 3 could possibly divide it. Therefore, since 9 is 3 and 3, right, 9 couldn't divide it if 3 doesn't. So knowing that 3 doesn't divide it, I can eliminate all multiples of 3. All right, so again, I am cutting my work way, way down, right? Because 21 couldn't divide it because 21 is made up of 3 and 7, right? So I'm starting to be able to really cross out a lot of potential divisors. I have to take my calculator out and divide it by 7. No other choice. All right, I have to take out my calculator, divide it by 11. All right, that didn't work. 13 didn't work. I would divide it by 17, I would divide it by 19. So notice I'm dividing, right? I would not have divided by 25 because if 5 doesn't go in, then 5 squared can't go in. So notice what I'm testing. The numbers in this row, if I said, well, what's special about these numbers that I'm circling? They're all the primes. All right, so that is the first step in making life easier. Okay, first step is that I only test prime divisors. Because all other numbers are composed of primes. Okay, so if that prime number doesn't go in, that prime divisor doesn't go in, so let me word it that way. When a prime number doesn't divide n, I'm going to call our number n, then no multiple of that prime could divide n either, right? That's because all multiples of this prime would be composed of that prime. Okay, so if n was not composed of the original prime, it's not going to be composed of a multiple of that prime either. Okay, then I hope there's other things you notice that would make your life easier. For example, if I took my n, which is 587, and I tried to divide it by, say, 23, all right? I got about 25 and some change, right? It's not a whole number answer, which is how I know it doesn't divide, but that would tell me that I could have a rectangle. If I could make my rectangle with non-whole numbers, I could have a rectangle where this is 23 and this is 25.52, right? If I could make rectangles with fractional pieces. Okay, so then if you kept going and you kept on testing, right? So I knew 23 didn't go in. I knew 19 didn't go in. Say I tested a number like 29, right? And then I take out my calculator, 587 divided by 29, right? And I get 20, right? So that would tell me that the other dimension of my rectangle was around, I don't get 20 on the nose, I get 20.24, right? So if I'm testing 29, its partner was back in here, right? So 29 partners with something around 20. So I start to realize, since numbers come in partners, right? Once I've tested all these numbers, right, their partners would have to be these larger numbers, right? So if I start dividing and testing all these larger primes, I would realize that if these numbers were going to work, they would have to have a partner that was down in here, right? Well, if nothing down in here worked, then how could these numbers be divisors, right? Because their partners would have to be down in this region, this range of numbers that I had already tested. So one thing that I want to remind you of is we took notes the other day on this fact that when we were listing factors and partners, we said, okay, so first of all, I'm going to say this, factors come in partners. One partner is less than or equal to, I wish I had the square root key. I don't think I have it here. So square root of n, the other partner is greater than or equal to the square root of n. Let me come up here then and say factors of n. Okay, so what that means for this problem then is I should take the square root of 587. Okay, square root of 587 is around 24. Right? That means I only have to test primes up to 24. I'm done right here. Okay, because I can see that 23, its partner's got to be over here, right? I can't have a divisor over here without a partner on this side of the blue line. Okay, so numbers, divisors before this blue line would partner with divisors after this blue line. If I don't have a partner on the left, there's no way I'm going to find a divisor on the right. Okay, there would be nothing for it to partner with. So therefore, adding to my notes on how to make my life easiest, I am only check for divisors less than square root of n. And on collected 4, you have to explain this. Okay, so if you come right back here on collected 4 and you look at some of the things we wrote down, and you can just, you know, add a little bit of appropriate verbiage with your explanation, then that will get you full credit for this problem on collected number 4. So right now, let's test this number. So pause the video for a minute and decide whether or not 493 is prime or composite by testing the minimum number of divisors. So actually list for me, you know, what are the divisors that you have to test. All right, and we want to test a minimum. So write those down and then decide whether that is prime or composite. So please pause the video for a minute and try this exercise. Okay, so coming back, if you took the square root of 493, you get 22, right? About 22. Okay, so what that means is I am only going to test potential divisors, I'm going to write about equal. I'm only going to test primes up to 22, all right, which means I'm going to test 2, but it's not even, so 2 won't work. And I'm going to test 3 by using that divisibility rule. Does the sum of the digits, is the sum of the digits divisible by 3? And it's not. Doesn't end in 5. I take out my calculator, divide by 7. 8, 9, 10. Next prime is 11, 13. Next prime is 17. And I think that's all I have to test, right? Because 23 is more than 27. So these are the list of the only numbers that I have to test. But you should have determined that 17 does divide this number, and its partner would have to lie on the other side of the square root, and its partner is in fact 29. So this would be no, this is not prime, right? 17 and 29 are the primes that compose this number.